All right, today we are diving deep into one of the most famous, most mind-bending, and honestly, most important experiments in the entire history of science. This is the one that completely rewrote our understanding of what reality even is.
Now, I know what you're thinking. That sounds like something straight out of a sci-fi movie, right? But what if I told you it wasn't just a thought experiment? This is a question physicists actually asked, and the answer they found, well, it shook the very foundations of physics. This one question is our key to the whole quantum world.
So to really get why this is so bizarre, we have to set the stage. We're going to look at the classic setup here, an experiment that is so simple in its design, but the results, they're just unbelievably profound.
And believe it or not, the roots of this whole thing go way back to 1801. A guy named Thomas Young used a similar setup to prove that light acts like a wave. And that was a huge discovery back then, but the real quantum weirdness wouldn't pop up until much later, when we could finally do this with actual particles of matter.
Okay, so this is just common sense, right? On the left, if you throw a bunch of sand at a wall with two openings, you're going to get two piles of sand on the other side. Makes sense. That's how particles work. And on the right, if you send water waves through those same two openings, the waves ripple and interact with each other, creating this complex pattern of peaks and troughs. That's how waves work. Totally different things, or so you'd think.
Now, let's fast forward to today. Because with our amazing modern technology, we can run this experiment not with a whole flood of light or a bucket of sand, but with single individual particles. We're talking one electron at a time. So picture this. We have an electron gun, and it's firing just one single electron. Then it stops. Then it fires another. And remember, an electron is a tiny fundamental particle. It's a little speck of stuff. So based on what we just talked about, we should expect to see two simple lines on the screen behind the slits. Easy.
And boom, there it is. The very first electron hits the detector and leaves one little dot, exactly like a tiny particle should. It landed in one specific place. So far, everything is behaving exactly as it should. No surprises.
So we fire another one. It lands somewhere else. And another. And another. Each one shows up as its own little particle, leaving a single dot on the screen. The pattern seems pretty random at first, but we're just getting started. We just let this experiment run. We fire tens of thousands of these electrons, each one flying completely alone, one after the other. And as all those little dots start to build up, something absolutely unbelievable starts to take shape.
And this is the whole mystery right here. We get an interference pattern. This is the exact pattern that waves create, not particles. The electrons, fired one by one, somehow arrange themselves into these distinct bands, with empty spots in between where almost no electrons ever land.
I mean, how is that even possible? For an interference pattern to happen, something had to go through both slits at the same time and then interfere with itself. But we were just firing one electron at a time. It's as if each electron all by itself went through the left slit and the right slit at the exact same time, and then its two possible paths interfered with each other to decide where it should land. It's just mind-boggling.
So, faced with this complete paradox, physicists did what they do best. They decided to cheat. They basically said, okay, forget this. Let's just watch and see which slit the electron actually goes through. That'll solve this whole mystery.
And the plan was pretty simple. All they did was add a tiny little detector right at the slits. A little sensor that would just tell them, yep, that one went through the left, or, okay, that one went through the right. Now we can finally figure this out.
But what happened next is where this story goes from just weird to, well, to fundamentally questioning the nature of reality itself. It turns out the universe does not like to be watched. The simple act of observing, of just looking to see which path the electron took, completely changed the result.
So look at this. When we don't watch, we get the wave pattern. But the instant we turn on our detectors to see which slit the electron goes through, the interference pattern just vanishes. Poof, it's gone. And instead, we get two simple bands right behind the slits, the exact pattern we expected from particles in the first place. Just by looking, we forced the electron to behave like a particle and pick a path, and it completely lost its wave-like nature.
So, what on earth is going on here? This isn't just a quirky little science experiment. This is a peek under the hood at the fundamental engine that runs our universe at the smallest scales. It reveals one of the core rules of reality.
The principle that explains this is called complementarity, and it basically says that a quantum object, like an electron, has these two complementary sides to it. It can act like a wave or it can act like a particle, but you can never, ever see both sides perfectly at the same time. If you set up your experiment to find out which path it took, that's a particle property, you completely destroy its ability to create a wave pattern.
Now, you might be thinking, okay, that's really weird and fascinating, but does this have anything at all to do with my life? And the answer is a resounding yes. This bizarre quantum rule isn't just some abstract idea. It is the absolute foundation of our most advanced technology.
I mean, think about it. The strange rules we just saw are the very bedrock of things like quantum computing. The wave nature of electrons is what allows electron microscopes to see things on an atomic scale. We are literally harnessing this deep, fundamental weirdness of reality to build technologies that are completely changing our world.
And all of this leaves us with one final, absolutely massive question. This experiment strongly suggests that at the quantum level, things like an electron's path might not even exist in a definite way until we measure them. It forces us to ask this wild question. Is the universe just a haze of possibilities, only snapping into one concrete reality when we or something decides to look? That's a question that physicists and philosophers are still wrestling with today.